Okay, so on page 10, we've got 3 different buildings or tabletops, whatever story you want to make, right? A and B have the same height, but a different launch speed. And this is a callback to what we did last time. It's a horizontal launch. So all 3 of these would have the same visual. You've got that parabolic trajectory, right? And then it's going to hit somewhere at the ground below. And so they've got different launch speeds. And then C has half the height and it has a launch speed equal to B. Everybody good? Yes. Oh, thank you. Okay. And so for rankings, who's going to be in the air the longest? Well, I have a question for you. I think last time I showed you the 2 billiard balls being hit and launched and then the bullets. Time depends on which axis. Okay, height is vertical, right? And so time, you got to think vertical. Now, if you're thinking, but it's in the horizontal equation. Yeah, time still exists in the horizontal, but time is vertical dependent, okay? So if you can, when you see time, start thinking plan A is always going to be vertical information. And so who's going to spend longest in the air? What do y'all think? A and B, which one's greater? They're equal. Why? Okay, so G is the same. What else? Height is the same. And then there's one more thing that's in every single equation. Well, other than time. Initial vertical velocity is the same. And specifically, when you have a horizontal launch, if you have no vertical advantage when you leave that building or tabletop, if there's no up, no down, if it's just straight out, what is that initial vertical velocity? What magic number? 0. Okay, and so because of that, A and B are the same. And then what about C? Is it the greatest? Is it the least? C is not the greatest. It would be the least. So A and B is greater than C. Why? Well, it has a smaller height. And if we think of the equation that ties all this together, that vertical displacement equals VIT, which zeroes out, plus 1/2 AT squared. The smaller the height, we got gravity being the same, but I'd have a smaller time. Now it's not a double, half, right? We saw that you've got a square value there. Think about the basketball picture we looked at, right? So just because it's half the height doesn't mean it has half the time, but smaller is true. Everybody good there? What about 2? Now that's not delta X minus range. Sorry if that was your interpretation. We were meaning delta X, AKA, we call that range. Horizontal distance that a projectile travels is your vocab definition for range. So what does range depend on? What's our equation for range? Horizontal velocity times time. And if you want to put in, oh, it's the second equation, don't forget that the horizontal acceleration is what? 0. So that whole thing goes away. The more you do this, you can just leave it off, right? And so it's based on horizontal velocity, which we see some difference, but it's also based on time. You can't forget your answer from before. So the answer to number 2 is not A is greater than B equals C, right? You want whoever has the greatest horizontal velocity and the greatest time. So who's the greatest? A. And then who comes next? B and then C, but no equalities here, right? And so B and C, they have the same horizontal velocity, but B is in the air longer. Good deal? And then 3 and 4 talk about V and then F, so final velocity. Number 3 has an extra subscript, Y. So here we're just looking at vertical. Now, what are these things here? What are those parallel lines? Absolute value. So we're looking at, yeah, it's going down. Some people will call down positive, some will call it negative, but we're just taking a speed type of approach, right? And so actually number 4 is your impact speed. We used that phrase last time, I believe, okay? Now 3 isn't really the impact speed, but it's a vertical component. Vertical, vertical. So who's going to have a greater speed vertically? Who's going to have a greater vertical speed the split second before it hits the ground? A and B are equal. I would agree with that. And it kind of is the same reasoning as we had in question 1, right? They all start at 0, they travel the same distance in the same time, and gravity is the same, right? So A and B will have the same vertical component, and then C would be the least. Again, same reasoning. It's got the smallest height, smallest time. But then what is 4 really saying? So 4 is that impact hypotenuse, okay? I don't know how to spell it. Hypotenuse. We'll go with that. And so when it hits the ground, no matter if it's A, B, or C, it's going to hit at some angle, right? Now, we're going to do a lot of SOHCAHTOA today. We're going to launch at angles. That's what's going to be the new part today. But y'all, it's not new. Here we have launch speed. We hit at an angle. That vector has a horizontal component and it has a vertical component. Now we just said something about the vertical component, right? What's true about horizontal velocity by the time it hits the ground? Horizontal velocity is constant. And so whatever we started with, 10 and then 6 and 6, they are going to still be 10, 6, and 6. But our answer is not either component. Our answer is who makes the biggest hypotenuse? So whoever has the biggest components will make the biggest hypotenuse, okay? Okay, so what do we think? Okay.
I'm going to give one of Ms. Meyer's students one of these real quick just so she can do an assignment, but I'll make sure it gets back to you.
Okay, thank you.
Yes, ma'am. Thank you.
What do we think? Who has the biggest components, the biggest hypotenuse? A. A had the greatest vertical and it had the greatest horizontal, right? 10 was the greatest horizontal. These are all VXs. And it had the greatest horizontal, vertical. Then who? Bless you. Who's next? It's B again, and C is the least, right? C has the smallest vertical component and the smallest horizontal component. And so B is somewhere in between. One of the components is one of the big numbers. One of the components is a small number. And so if you were to Pythagorean all those values, you should get A with the biggest hypotenuse. Good deal on there? Okay, so that's horizontal launch. And while we're here, let's go ahead and do our first or second. I think we had started an angle launch with the baseball problem. We'll go back to it, but let's start with this one. We'll do this one together. So at the bottom of page 10 there, we've got 3 balls, objects. We don't really know what they are, but we're going to launch them at the same impact speed. I'm sorry, launch speed. Now notice you're not given a number. So I'm just adding that these are launch speeds. Notice the arrow, right? We're not hitting the ground, we're leaving the ground. And so here's the new part. Instead of ending with trig, we're going to start with trig. Each one of these launch speeds has a different angle. So let's do a little geometry lesson. 10 degrees is closer to the x-axis, yes? So it's going to have the largest Vx. 45 degrees is still has some horizontal, but it's not going to be as much as what 10 degrees yields. And then C at 60, we're getting even further from the horizontal, so it'll have the smallest horizontal. Everybody good there? So as angle increases, get a little trend going. As angle increases from 0 to 90, Vx decreases. What about the vertical direction? And so go back to A, we're at 10 degrees. Well, that's close to the x-axis, not very vertical, right? Now notice I'm putting an I on that one. I didn't on horizontal because constant velocity, but vertically, you start with an initial velocity and gravity is going to change it. And then 45 degrees, well, that becomes more vertical. And then 60 degrees is even more vertical. And so as theta increases, what happens to VIY? It increases. Now we'll get into sine and cosine coming up, but right now, just knowing that kind of trend, okay? So who spends more time in the air? Time is what axis dependent? Vertical. So think about our vertical. I'll stay with red, right? And so think vertically. Who does it take gravity the longest to slow down on the way up and then maybe speed up on the way down? We'll assume that all of these are like going to come back to the ground at some point. So it makes that very nice parabolic motion. So who's going to take gravity longer to slow down and speed up? C. Who would come next? B. And then A at the end. And to keep that going, yes, vertical motion. And so if we are going up to the peak, so I'm going to break our path, okay? And so from ground to peak, we could base it on this equation, right? Time in the air, time to the peak. That would get the same answer because we're just looking at half the picture. Gravity's the same. And whoever's going to have, they all have the 0 with the peak, right? And so acceleration is the same. Whoever has the greater initial vertical velocity is going to spend more time in the air. And that may look a little weird, but remember, gravity's negative to slow it down, right? So if your V initial is bigger, you need to subtract a bigger number to get 0. And then you could do the same for on the way back down. What about height? What axis? That's a vertical. And so we just found something about time to the peak. Isn't that the distance to the peak? And so that's like your delta y to the peak. Well, we know that time is going to be similar, CVA, gravity. And then we know the final velocity is 0. But instead of using that first equation, let's relate it to a displacement. And so what do y'all want to use? The second or the third? Second. And so we'll base it on delta y. And again, we're just going to the peak equals that VIYT plus 1/2 AT squared Now that one has time in both places, so that one could get tricky. We know that this is our -10, and VIY, we know is going to be greater and time is greater. That one's too much. Let's do the VF squared. Too many moving pieces to that other one. So we know gravity is the same. At the peak, we know they're all going to have 0 final velocity. And so again, with gravity being negative, it doesn't appear like it should be this way. But the bigger the initial velocity that we hit it with, the longer it's in the air, the more distance it's going to go. Because remember, gravity's negative there. So you want to subtract a bigger product. Does that make sense? So our final ranking would be same as time in the air, CBA. And then we come to range. Range, what equation are we going to use for range? We used it up above. Delta X equals your horizontal velocity times time, right? Who has the greatest horizontal velocity? Look at our vector components up above. A has the greatest horizontal, because again, 10 degrees is closer to the horizontal. Who has the greatest time? C. Uh-oh. We got a conflict there, right? Kind of hard to determine. Let's go to a simulation. I want to show you something pretty neat, pretty neat. So let me get it pulled up. Get my keyboard back on. And by the way, I will copy this simulation website into OneNote. And so it's PHET, P-H-E-T. Oh, let me do my new share. And so PHET, we're going to do the lab-based portion. And so you can actually like do some collecting of data here and look at trends, but we're just going to use this to see what happens with a high horizontal velocity compared to the time in the air. Who's going to give us the greatest range? And so I'm going to keep with all the defaults. It says I can change the mass and the diameter, but as long as I turn the air resistance off, which it is, then it won't matter. So I could come here and turn it on, but I'm going to leave it off. I'm going to leave gravity as Earth. And so we'll go to that. I can't go to 10 degrees. This simulation, 25 is the lowest, okay? So it's less than 45. Can we get the spirit of an angle less than 45 here? Sure. So here we go, fire in the hole. Now, we're not target practicing here, so don't worry about that target along the bottom. By the way, this is very similar to the lab that we'll do, hopefully next time or the time after. We got a marble launcher lab to do, and so you'll have a target, and hopefully you hit the target, right? And so there's 25. Everybody good there? What if I move it to, what was the other number? Not 45, but 60? Let's do 60. That one had the greatest time and the smallest, so I didn't change the initial speed. And so even though we don't see the components there, I raised it up closer to the vertical. And so horizontal component of the 18 meters per second should be less. Fire in the hole. So if you can see behind there, I can't move the control panel, but it went behind it and landed further. Okay, and then there's 45. 45, fire in the hole. You ready? I guess I should have asked you to make a prediction. Most people say, oh, it's going to hit in between. But if you follow along, where does 45 hit? The furthest, right? It turns out when you kick a soccer ball, when you throw a football, when you want to make that ball go as far as you can, hit a baseball, you want a home run, right? You want to do your best to hit it at a 45-degree angle. Note to self, 45 degrees is your optimal angle for greatest range. And why? It's that nice in-between type where it has just enough in the vertical and just enough in the horizontal. Angles less than 45, they end up not really being in the air as long, okay? The horizontal might give them an advantage, but they're in the air less time. And then your greater angles are in the air for a longer time, but now they have the disadvantage of not having as much horizontal velocity. So it turns out 45 is your optimal angle. And so we'll do now let's do it now. There's one more thing we can do here. 60 degrees that we were once at, what if I bring it to 30? That's an angle I haven't done. 30. So watch this. Fire in the hole, 3, 2, 1. Follow it. Where did it hit? Where 60 hit. So 30 and 60 have the same range. 30 plus 60 equals 90. Angles that add up to 90 are called what? Complementary angles. Well, let's test this with 25. I started with 25 degrees. What's the complementary angle to 25? 65. So let's go to 65. Oh, there we go. Fire in the hole, testing our complementary angle. And it lands in the same place. So again, this is without air resistance, but it turns out complementary angles, as long as everything else stays the same, I didn't change anything but the angle. They have the same range, okay? 45, 45, well, that's already built into itself. 30, 60, 25, 65, any other complementary that you can come up with should have the same range. But the greatest range is closer to 45. So the closer your angle gets to 45, then the greater the range it has. And so, who has the greatest range? Oh, hold on. OneNote does not like it whenever I switch back and forth, I've discovered. There we go. So greatest range would be who? B. And then, is it 10 or 60? I wasn't able to test 10. It would be 60. Why? Right, it's the angles closest to 45. Okay, and so C and then A would be the least. So closest to 45 and then furthest to 45. Good deal? Yes, leave your phone. Okay. All right, what about this last part? Impact speed. And so they're going to go up at some angle. We said that's the launch. Now we weren't given a picture here, but what should happen? It's going to come back and hit the ground and land at some impact velocity, impact speed, right? Now I drew this picture very as specific as I could there. Do you see the symmetry? Horizontal velocity is going to be the same all the way throughout, even at the peak. Okay. Vertical velocity, we start with something, and then at the peak, we have a split second, 0, no vertical component. And then we got to travel the same distance down, the same height down. What's true about the final vertical velocity? Gravity slows us down over a set vertical height to 0, and then gravity speeds us up from 0 from that same height. The symmetry is it equals your initial, but now it's negative. You're going downward. And so it's this symmetry of the vertical plus the constant motion in the horizontal. Launch speed equals your impact speed when you have y initial equal to y final. Or another way to write that, what's your change in your vertical displacement if you end where you start? You start on the ground, I end on the ground. Vertical displacement, start to finish, is 0. And so when that is true, then your impact speed at the end is equal to your launch speed. And on this problem, since they all started with VVV, they all end at VVV. Yeah, different angles, but they have the same or all equal. VVV, right? That's what was given. Questions on launching at an angle. We looked at components, okay? Components is going to be a key word whenever we do forces and velocities at angles. Okay, well, let's go back. I think page 6 was that baseball example. Nope, page 8. We'll finish this one. And some of the big ideas we already talked about, so yay. We get to draw some graphs on this one. And so we'll read the prompt again. We'll kind of start overish. A baseball is thrown from point S that's in right field to home plate. And so notice our right field, our S is going to be on the right-hand side, and then home plate is on the left-hand side. The dashed line shows the diagram. In the diagram shows the path, and remember it's a parabolic trajectory. Those are your fancy words. Use the coordinate system as up as positive vertical, and then to the right as positive horizontal. Is our ball going to the right? No, the ball is moving to the left. So if right is positive, to the left is negative. So they have defined the positive direction standard, but our picture is not going in the standard direction. And it says the origin is the point at which it was thrown. So that's like your 0 meter. That's where everything's measured from. Everybody good? On the axes below, sketch the graphs for the indicated quantities. And we already did take a look at the velocities. It's the same story as what we just went over. The horizontal velocity is constant, and then the vertical velocity decreases on the way up to 0, and then it increases. And notice we're catching it at the same vertical position. So the final vertical position is equaling the initial, and so that final component is equal to the initial vertical component. Draw the horizontal velocity versus time and the vertical velocity versus time. So tell me about the horizontal. This one should be the easier one. Horizontal velocity is constant, so we know that. Now, your first gut is to go, boom, quadrant 1, done. Wrong today. What should it be? Going to the left. They said right was positive, so we need to make it negative and constant. So this is our Vx, and it is negative because we're going to the left. Good there? What about the vertical velocity? We start going what direction? Up. We end going down, they said up is positive. So maybe we start with a positive initial vertical velocity up. They defined up as positive. And then at the end, we got a little symmetry going on. We're going to have the same magnitude. So ish, same spacing, but maybe at the end of our time, and this is a negative final velocity. And just so you know, it's equal to that initial velocity in terms of magnitude. We got that symmetry. Now, how do I connect those two? Straight line, and it should cross the axis if symmetry is playing a role. Where should it have v equals 0? Halfway. So halfway-ish we see, so about half the time is when we reach the peak, right? And vertically, you come to a split-second stop. And so should be a straight line. Another reason for the straight line is what? What does the slope of this line give you? Acceleration. And for an object flying through the air, specifically, it should give us G. And they said up was positive. G pulls down, should be negative slope. Okay, it should agree. All right, what about the acceleration graphs? We just said what in the vertical? Let's do that one first. We said you have negative G for the acceleration, right? Or slope, it's a constant velocity slope, right? And so we should have negative G, constant and downward. And then what about horizontal? Horizontal acceleration? A big fat 0, constant at 0, right? Neglecting air resistance. Okay, I think we got one more page of concepts, another ranking, and then we'll start doing some calculations. So make sure someone at your table has a calculator. You have 5-minute warning. Okay, page 9. We got launching at an angle. And so that's the kind of new piece today. We're not starting in one direction. We're launching in 2 dimensions. So we've got cannonballs of 2 different masses. Well, first of all, does mass matter to projectiles, to kinematics when we neglect air resistance? Nope. So who cares? Ignore the masses. Later with forces, mass will play a role. And it says we project them upward and forward. Okay, so those are kind of our positive directions. The cannonballs are projected at various angles above the horizontal, but all are projected with the same horizontal component of the velocity. And they actually show you those 20, 20, 20, 20, 20, 20, right? So they've all got the same horizontal, but notice they're at different angles. And if you think about SOHCAHTOA, they would all have different hypotenuse, right? Rank according to the horizontal distance traveled by the balls. Well, forget the ranking. Let's get into justifying first. And so horizontal distance, AKA, what's our vocab word? Range, delta X, it's equal, what's our 99.9% of the time equation? Delta X equals, right, horizontal velocity times time. Well, horizontal velocity is all the same here. So does that mean they all have the same range? No, it depends on who has more time. Notice this is a direct relationship. And so there's a direct relationship. So I'm doing my justification first between time and range. And so who is in the air longer? Well, how are we going to determine who has more time in the air? Kind of, sort of. Yes, kind of, sort of angle, but more specifically, time is dependent on which axis? Vertical. So really, we're looking at the vertical components that are not labeled, right? So it does relate to the angle. So what angles are more vertical type, right? Because the more time in the air, you're going to have more time. You need a bigger initial vertical velocity. And the equation that you could use there is that VF to the peak equals that V initial Y plus AT. And so at the peak, vertically, they're all 0. Gravity, all the same acceleration. And so the one who's in the air the longest, and again, gravity's negative, so you need to subtract a bigger product from a bigger initial velocity to get that 0, right? And so whoever has the greater initial vertical component is in the air the longest, and whoever's in the air the longest with the same Vx will have a greater range. Kind of a two-step thought process. And so, final ranking, who has the greater vertical component? Which is the unlabeled one. Uh-oh. Y'all need to wake up. Who has the bigger vertical component? Who's got the bigger vertical component? There we go. E is equal to F, and then who? C and D are equal, and then A and B have the smallest, okay? So E equals F is greater than C equals D, which is greater than A equals B. Good deal? And so you may be wondering, well, how did you know? And so again, they were unlabeled. They all have the same horizontal component, but different angles, right? And so your 60 degrees is in the more vertical, and so it would have the greater vertical components. Or you can actually do a little math that we're about to learn. Okay, then we come to page 11. And so we got at least this top one. We're going to do number 2 today. We'll do the bottom one next class. And then I think on page 14 or 15 is one y'all are going to try. So we got a football kicked at an angle of 37 degrees. Now you may be thinking, oh, 37 sounds so random. Actually, it's going to give us some nice numbers. And I think it's unit circle or something. If you look on the front of the formula chart, they actually, AP does give you some of the common angles they use. So 30 and 60 and 45, those are nice. But 37 and 53 are actually quite common as well. And so if by chance on the May exam you forget your calculator, you don't have to do sine, cosine, and such in your head. They actually give you the equivalents of sine 30, cosine 37, all those common angles. And so 37, although it sounds random today, it's really not. So we're going to kick this football at 37 degrees with the ground. Usually it's wherever the object originates. We don't put the football on the vertical, we put it on the horizontal ground. And we kick it at a velocity of 20 meters per second, or that's our launch speed, okay? Assume the ball leaves his foot at ground level. In other words, you know, when a kicker kicks a football, maybe the foot is a meter above the ground, right? We're neglecting that 1 meter, okay? Make our lives a little easier today. 4 things. What is the maximum height that the ball reaches? Height, we're thinking vertical there, right? The time it takes for the ball to hit the ground again. Time is dependent on which axis? Vertical. And so I'm just kind of getting thoughts down as we go. And then how far away does the ball hit the ground? AKA, what are we solving for? What's our vocab word? How far away? Range. And so we're solving for range, or it's a horizontal displacement. And so those are the 3 things that coming up we're going to solve for. Why am I doing that? We're going to do D first. We're going to put our picture in part D because D says, draw the velocity and acceleration vectors, arrows, at the maximum height, at the peak, okay? And so I'm just going to draw the whole picture here. And so we've got our ground, level ground, okay? Football, whatever it is. There's our football. Now we don't care about the kick. The kick comes later. That's forces, right? We're looking at the split second it leaves the kicker's foot. That's the first moment it's a projectile. And they said neglect that height. So we're just going to say, well, let's launch it at this speed, okay? At this angle from the ground. And that football is going to go up, 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 up to the peak. Does it stop forever and ever and ever right there and fall straight down? No, it's got to come back down, but it's going to finish that parabolic path. Okay? And I'm trying my best to draw like mirror image because this one should have some symmetry. And it turns out later, we'll look at that impact speed. Okay? That's our impact speed, launch speed, impact speed. Well, they're asking about the peak. And so that peak moment, it doesn't totally come to a stop. Vertically, it does not have velocity, but what direction does it have velocity? Horizontal, in the forward, or as I have it drawn, to the right. And that horizontal velocity is drawn tangent to the path. It touches just at that one point. And hopefully it's equal to the x component of your launch speed and the x component of your impact speed. So all those red horizontal arrows, and yes, one is solid, 2 are dashed. The beginning and end, those are components. But there at the peak, the velocity is the component. So it's all of it, okay? And then they want the acceleration. Now the whole time, it doesn't matter where the ball is, acceleration in the horizontal is 0, and acceleration in the vertical, we'll go with standard sign convention, -g or -10 later when we calculate. So how do I draw that on the picture? Well, they said draw it at the top, so we'll just, the ball at the top, we got -g. Technically, it's already downward, so you just need to put G or A subscript G, either way. But true story, every point along the path would be the same -g. Gravity doesn't change as the football goes through the air. The velocity does, but the acceleration does not. Good deal? So hopefully that's not too brand new for you. The new piece is going to become how we start the problem. And so previously, when we drove our car off the cliff, again, no one gets hurt in physics land, okay? But now, instead of starting at the peak happens in the middle of our time frame, right? Wouldn't you agree on that picture? That if you were to cover up the first half, that's what our car did? So in your mind, cover up that first half. That's what last class was about. So we started vertically at 0. Today, we do have an initial vertical velocity, right? That VIY. And I'm going to redraw that picture up above, at least that starting point. And so our initial velocity in the vertical is not 0 anymore. But what is true, what is 0, the velocity at the peak in the vertical direction, or peaky velocity, because that's fun, the peaky velocity is 0, okay? And so what maximum height does the ball reach? We said we want to think about the vertical stuff. So let's think, what do I know vertically? We know gravity. We'll go with -10. Height, that's really the vertical displacement. So that's what we're looking for. What else do we know vertically? Peaky. If I'm just going up, kind of pause, hit pause on that simulation, then the peak velocity becomes 0. And is it initial or final? It's final. And so the final velocity is going to be 0. And just note to self, I'm pausing at the peak. So just imagine that simulation, pause. It's final. And so what's the initial vertical velocity? The answer is not 20, not 20. Here comes the new part. We're going to start with that SOHCAHTOA. So the 20 meters per second is what's actually happening, and you're actually kicking it at a 37-degree angle. Well, that hypotenuse, what's going to come, the hypotenuse, it's not horizontal, it's not vertical, it's neither, it's both. I need the components. And so I have a horizontal component that, looky look, is adjacent to 37 degrees. And you have a vertical component in the beginning, because this is at the kick, which is opposite our 37 degrees. And X and Y, they are always 90 degrees from each other. So that 20 meters per second is your hypotenuse. And so how do I figure out, if I know the hypotenuse and the angle, how do I figure out that initial vertical component? Which trig function? Uses hypotenuse and opposite. Sine. And so we come in, sine theta equals, I'm going to write it as opposite over hypotenuse. Formula chart uses like A over C. They define A, B, C. And so now, opposite is what we're solving for. So you can multiply. This is just an equation. Multiply both sides by hypotenuse. And so it turns out the opposite, or VIY, is equal to the hypotenuse times sine theta, or that launch speed, or just initial speed, times sine theta, okay? And I'm going to highlight that one. That's a very common starting point. Now, I don't want you just to blindly start every problem that gives you an angle this way. This only works out if the angle touches the horizontal. There is the rare occasion that maybe we bounce a ball against the wall and it has a vertical, right? And so, and later on with forces, maybe you have some kind of vertical reference point. But most of the time, to find your components, the vertical is found with doing the sine theta. And so let's plug in some numbers. Hypotenuse is 20. sine 37. So now somebody at your table has a calculator, hint, hint. Before we punch these numbers in, what did we learn last time? Our calculator needs to be degree mode. Big time, big, capital, bold, underlined, right? Highlight. Okay, I'm just telling you now, don't be the person who takes the exam on September 29th with your calculator in radian mode and then email me an hour later, ooh, can I take the exam again? I took the whole thing in radian. Cross your fingers for partial credit, right? That's why we like the free response and like that it takes a little while to grade. I'm trying to give partial credit where I can, right? But make sure you get in degree mode. And I promise I'll do my best to remind you before the exam. Now that you're in degree mode, 20 times sine of 37, give me the rounded number because it comes out actually pretty nice. 12, 11.99, whatever it is, it's 12. And that is not our final answer, but that is going in my vertical information. Don't calculate 20 meters per second with the 9.8 or 10. But now we know the initial vertical velocity is 12 meters per second. Now, what equation can we use to find that vertical height? So on the left-hand side now, we have our given. Notice we don't have time yet. So, say it again. We could solve for time, but we don't have to if we use what equation that doesn't have time in it? The third equation. And so I'm going to try and squeeze that in here. I'm kind of writing all over the place. VFy squared equals V initial y squared. Now we know why those secondary subscripts are there, right? You got to have direction. Plus 2a delta y. And so final, remember we hit pause at the peak, so 0 equals 12 squared plus 2 times negative 10. There's our delta y, 140, no. 12 squared is 144. And we got to subtract it to the other side, right? And then we got to divide by negative 20. So what's 144 divided by 20? The negative ends up going away. What do we get? $144 divided by 20. I told somebody to get, oh, you're good, 7.2. That sounds familiar. Okay, and you get a positive number as you should, right? We're going up. We started on the ground, we're going up. And so there's your final answer for part A. That vertical displacement traveled is the max height. Or we could have, if you're like, oh, I hate the third equation, I never want to use it again, right? We could have come down here and done B first with one little modification. Look at B. What is the time it takes for the ball to hit the ground again? Now, if you remember the picture, I said it's symmetric, right? So you've got this on the way up to the peak, and then on the way down, you got a time up and a time down. The max height is really just half the time. So if we had solved for half the time, then we could have found the max height, right? Here, we can still solve for half the time, right? Find the time up to the peak now that we know the distance. How would I find time down? If it's symmetrical, they're equal, but they want the total time. They want the time it takes the ball to hit the ground again. And so one way to solve this problem is to find the time up and then just multiply by 2. We're going to do that, and then I'm going to show you not necessarily a harder way, but a kind of cool way too. And so let's find, using all that same information up above, we now know both velocities, we know the acceleration, and we know the displacement in the upwards direction. So we can use the first or the second. What do y'all want to use? First one, yeah. And so we show the grader, what equation we're using, right? And we're pausing at the peak. This is only the half time. Don't forget, don't put in 20 for the initial velocity. You got to do the component, 12 plus a -10, and this is time up. And so what is time up? Well, subtract 12 and then divide by -10. Negative goes away, as it should. Time should never come out negative. And we get what? 1.2 seconds. That's not the total time. Total time would be 1.2 times 2, or 2.4 seconds. Good there? So if we'd done that time up first, then we could have used maybe the second equation to find the height up, okay? Let me show you an alternative to that one, because I at least want to show this to you once. This one's not as, apparent at first glance, but it's kind of cool the way it works out. So we start on the ground, we end on the ground. Forget the peak. Ground to ground. What is your vertical displacement start to finish? 0. And just note to self, you get that by saying ground to ground as your initial and final positions. Well, the same things are still true in terms of acceleration. And the initial velocity is still 12. But can we find time without that final velocity? What equation does not have final velocity? Second one. So delta y, I'm going to put it in terms of, equals VIYT plus 1/2 AT. Don't forget to square. Well, notice when you are ground to ground, and I have 0 here, equals 12t plus half of -10 t squared. That half of -10 or -5, can't I add 5t squared to both sides? So move that to the other side. And you may be thinking, oh, this is going to be quadratic, right? T squared and t, but we don't have a c term. At this step, what can we do? T squared on the left, t on the right. What if we divide both sides by t? We get one set that cancels out. And so 5t equals 12. What's 12 over 5? 2.4. And so that also is a way to get total time. It's not as apparent since delta y zeroing out, right? But it's pretty, to me, it's pretty neat that it works out, okay? All right, one more. I think we can do it. How far away does the ball hit the ground? AKA range, horizontal. It's just that horizontal velocity times time. And to hit the ground, that's a total time, right? We don't want half the range. And so that total time we now know is 24. What do we put in for the horizontal velocity? 20? No, that's the hypotenuse. Have we found the horizontal component? No, but now we can. We want Vx, which is adjacent. Hey, we could do Pythagorean theorem to solve for that one last side, or we can use tan, or we can use cosine. I'm going to use cosine because that's what textbooks typically use. And so down below, notice it's adjacent. And so we can say cosine 37 equals that horizontal velocity divided by that initial velocity. Multiply both sides by initial. Vx is initial times cosine 37. And again, most times when your angle is with the horizontal, you'll use cosine, okay? And so that 20 cosine 37, punch it out, what do we get? Should be a nice number when you round it. Don't everyone reach for the calculator at once. About 16, so like 15.97. Who cares about 3 cents? We're going to go with 16. And so 16 times 2.4 is a final range answer of 16 times 2.4. Oh, it's 15 instead of 16.
No, I'm just saying it's like.
Okay, well, give me the answer and I'll let you go. 38. Okay, no, that makes sense. 32 times 2. And so 38.4 meters would be your final range, okay? All right, apparently it's lunchtime. Forget about the bell. Okay, so maybe y'all need to eat something to wake up, huh? Next time, Thursday, we'll keep going, but maybe we don't always have symmetry. All right, y'all have a good day.